I mentioned in the introduction that heaps are often implemented using an array. And that logic might not seem intuitive at first, but with a few simple concepts, I think you can see how elegant and simple it is for a heap to be used in an array. And again, if you remember why we typically only have a limited number of items in the heap, it makes perfect sense to arrange it as such. So the foundation behind this, the idea of an array being used to store a full tree. A full tree meaning that I have a left side and a right side of a binary tree, and every single tree has a left and a right node to it. Now, it doesn't mean everyone forever, but you can see in this case, A through O, I have A has B and C as children, B has D and E as children, D has H and I as children, and then those are the leaf nodes, and they go all the way across, and every single one of them is full. And when we say full, it just means there's storage set aside for them. Um, Notice here, there's a nice symmetry to the data, and I've color coded it on the side here of what the array might look like. So the top node A is at location 0 in my array. And then from there, I have two nodes, which I've color coded the orangish color here, B and C, which are the next level of the tree going down. And then D, E, F, and G are the next level below that, which again, there's a symmetry in that B equates to DE, C equates to EF. So they go in order left to right across the tree. And now notice it's one node, two nodes, four nodes, eight nodes. The next level would be 16 nodes. And so it grows exponentially in powers of two. And so the basic structure maps over. And even if I didn't have, let's say in this tree, N and O, there would be data storage set aside for that. I would just have empty values down here. And so I normally would build the array to be based off of how many levels I want to store. In this case, I'm storing 15 values. If I add another level, I can store 31 values. I'm sorry, yeah, 15 values. I add another level, I store 31 values, and then I add another level on top of that, then I essentially double it again, and keep going. Um, so, given this data structure, um, how do I know where to find this relationship, these lines inside of here? There's no physical lines inside of here. They're all sitting next to each other. Again, it's an array. So if I consider E, E is a yellow node right here. It's at the level 2, so A being level 0, B, C being level 1, D, E, F, and G are level 2. If I want to know what the parent node of it is, well, it's B, the orange level, which amounts to the mathematical formula of the index minus 1 divided by 2. And we talk about this as integer division. We don't get partial numbers. So if I did it divided by 2, then my parent would be C. So that's obviously not correctly done giving this formula. So I just take 1 away, and that takes me down to 3. Divided by 2, that is 1.5, which gets floored down to 1. I just throw away the decimal portion. Um, Again, if I want to know what the parent node of G is, for example, 6, it's not 3, it's minus 1, 5, divided by 2 is 2.5. Throw away the remainder, I end up with 2. So it works out fairly easily. And going the other way, if I want to know what my children are, well, the first child, J, down at the green level, is 2 times the index, so 8 plus 1. And then the other one is 2 times the index plus 2. Or 2 times index plus 1, because it's the transitive property of multiplication inside of there. But we can easily navigate between the top and bottom of the tree by just simply doing a little bit of math. And this is not unlike doing the pointer jump inside of there. So it's basically, when we do that pointer jump, I'm just storing each value separately. Well, here I don't need to store the address. The address is just the relationship that I do between the math. Like everything in data structures, there's a trade-off. The tree in a traditional structure stores more data, which is the address of where I'm going to. The array implementation of a tree stores less data because I don't need to store addresses, but I need to do real-time math operations to figure out where it's at. So again, the analogy being, I could either say, oh, you live in this Happy Dales subdivision, and you're the sixth house on the third street. So I don't know what your street number is, but I know that if I start at the Happy Dales, I go to the third street and near the sixth house. Or I could say your address is 456 Main Street, and I can just write that down and do it. That's kind of the two options of how we can build these trees. But this mathematical option works well because we know we have a fixed size that we want to be able to grow up to for our priority queue. If our queue gets too large, I can't possibly keep up with it. And so I can set the size of the queue I care about. So how do we add things? Well, like all lists, we just start with an empty tree and we add it. So our array, it's the full size, but I'm just showing you the first step because that makes my animation easier here. But when I add B, it always goes in the next location, just like an array list implementation. C, again, goes in the next location. D goes in the next location. So just like as we said in an array list, I always put it at the end for the size of the numbers we've added in. And we just keep doing that all the way through. Now, since these are coming in sorted order, it's a min tree right here, A, B, C, D, E, where they all get bigger than each other, I don't have to fiddle with the tree at all. They're always correct. But that's not realistic. So we know for a traditional tree structure, this is a problem. It makes a very poor tree structure. But for the min or max, it's actually perfect. It works out quite well if it comes into a line with the data structure. But it rarely does that. So let's talk about a more realistic insertion. In a more realistic sense, when I add an item like A, well, I always insert it at the last item. That's the rule you need to remember. It always goes to the end of the array, end of the list, if you will. And then I bubble it up. Sometimes this is called floating. Sometimes it's called swimming. Sometimes it's called swapping. But the idea is it bubbles up to the point where either I am in the min tree less than and a max tree greater than the nodes, but still less than the ones above it, or I get reached to the top because I'm the most important thing that came in. So clearly, A was it was less than I, and so A and I also traded spaces over here in the table, not just the visual representation. It moves up again. A was less than E, so A trades places with E. It's jumping way up the table now. I'm almost at the top. And then A is also, so I'm recursively checking these or iteratively checking these, depending on how you write the algorithm, until I reach the top or I found my place in the data structure, in the heap. So this is heap ordered items now. Notice here, it doesn't necessarily mean, like Y over here is still greater than M and S and X for that matter, for sure. It doesn't matter that it's structured like that, so long as, in this case, I am less than my parent inside of here. That's all that matters. But if I want to go find, why, I don't know. Do I look at the left or the right? It's very inefficient. I essentially have to look at everything like I would in an array list or a linked list. So the insertion is pretty straightforward. The searching is not so much. But we can be very effective in the removal. So the removal of the heap always happens from the top. The top of the heap always has the highest or lowest value, depending on what type of heap I'm trying to build. So what I do is I start by swapping the top and bottom. So then I could easily take out the last item. So M goes to the top, and then C goes to the bottom, and C is available to be taken out at that point with essentially no cost. But I've messed up my tree order. I've taken something that may or may not be the highest priority next item, and so I've got to figure out, well, it needs to go down. It's called sometimes sync. So am I going to go left or right when I sync, though? Which child is the lesser one? Because remember, I need to make sure I keep this in the proper heap structure. So if I move F up, F is less than E. That doesn't make any sense. But I know one of the two of my children are the lowest out there. So I have to compare them and see which one's less. So it was E, and so I swap it with the smaller of the two children. And so E goes up to the top, smallest stays on top, M moves down, and I do the process again. So which one is smaller? I or Y? Well, I is smaller. So I moves up and M sinks down until it either reaches the bottom or it reaches the place where it fits. It's greater than its children. So at that point, the last one is easily removed and returned to the user. So I mean, where I remove it or whatnot is unimportant. But the great thing about this is all I have to do is shrink the size of my priority list by one, and my array gets a little bit. My array stays the same size, but my index in the array gets a little bit lower, and the next time I add it in, it starts again at the back, at the bottom. So heaps are a wonderful middle ground of efficiency. We could optimize this sort of approach in several different ways. We could optimize it for inserting, where we always throw it at the end. That's what we start to do. And then we search for the item that's smallest in the whole data structure. That's what you would do if you were making an array list. That searching takes a lot of time. So an array list is really, really fast to add things in it. We just throw it at the end. But when I want to go find the min or the max, I could end up searching through every item in the list. I kind of have to make sure that I get the one that's really truly the minimum. I could optimize it for deleting, where removing the item, where essentially every time I insert, I sort it so that way the item I delete is always at the back end of the list. So the delete is instantaneous. Boom, take it off the back. But then inserting becomes slow because I have to end up moving everything around and sorting every time. And we'll talk about sorting algorithms more in detail as it comes up. So what the heap does is it instead makes a little bit of effort that I have to do when I insert things. I insert at the end and then bubble them up. But I don't have to touch everything. I just simply have to touch that one basically a logarithmic number of times. So it's half of the structure, but less than that because I don't even need to look at all the half of the structure, right? I only have to look at 2 to the n. I only have to look at it up to that n times, so that the number of nodes inside of there that's creating the structure. So in the tree we just saw, at most I had to do it 3 times, right? And then deleting, similar. I get the value quickly, and then I mostly have to bubble it down logarithmic n time. And again, we'll talk about this idea of logarithmic calculations more. I want to say it now so it means something when we get there. But we'll really dive into how we analyze the efficiency of data structures, in a couple of weeks as we really start to understand these a little bit better. All right, so that is how these work, and there's some other videos I can link you to if you really want to start coding these and playing with them. So then the next video you'll see is an overview of the assignment we're going to do this week. But then after that is going to be some videos from some peers, some friends of mine who have also taught this class, who focus a little bit more on the coding side of it. Again, it's not that I don't want you to focus on the coding side of it. I'm just not going to create a video at this point that is maybe not even as good as what they're presenting, and certainly is not something I'm expecting you to code at this point in this class.